Namaskar everybody. I am Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dausa, Rajasthan. This is my lecture number 28 on the subject engineering mechanics. Today we will be dealing with the analysis of moment of inertia of composite sections. Let us see what we learnt till today in the subject moment of inertia. The mass moment of inertia, it is the inertia against turning moment, which is also called torque. It is similar to the inertia against the rectilinear motion. Area of moment of inertia, it is the resistance of bending moment of a beam. It is the resistance offered against bending by the beam. Is the more the moment of inertia, more it will resist the bending moment. For the same bending stress, it can resist more bending moment if its moment of inertia is high. It is the second moment of mass, meter mr square, or second moment of area ar square. Its unit is meter to the power 4 or kg meter square. For mass moment of inertia, its unit is this one, and for the moment of area, its unit is this one. For the area moment of inertia, you can say that in the subject strength of material, we will be dealing with the bending equation m upon I equal to sigma b upon y equal to E upon R. In that case, you can say that for the same bending stress, this you can say it m is proportional to I. Basically, there is a section modulus term that is denoted by Z equal to I upon Y. So m is proportional to Z. But we can roughly say m is proportional to I also, in the same way. So, for resisting maximum possible bending moment, we require a section which having highest moment of inertia about the same axis of reference. I am leaving it here only. When we are dealing with this topic, we will concentrate there. Now, perpendicular axis thought. Again we are discussing it. It states that if a plane, this is the plane, that it's having two centroidal axis xx and yy meeting at point O. An axis which is passing to the point of concurrency here and which is perpendicular to both the axes. The moment of inertia about that axis, considering that this axis is z, then Izz equal to, or Iz, we can say Ix plus Iy. Proof is very simple here. This is the proof. We have done that. We know that the distance of that vertical axis from the elementary area dA is r. Then by applying a Pythagoras theorem for the right angle triangle, this we can say r square equal to x square plus y square. Multiplying both sides by integral dA, that is total area, it becomes r square integral dA equal to x square integral dA plus y square into integral dA. So this is your Iz, this is your Iy, and this is your Ix. This is your Iz. It is very simple. So Iz equal to Ix plus Iy. And this for a circular say cylindrical member. It is a cylindrical member like this. Then this ZZ axis will be called as centroidal or polar axis. Why we call it polar axis? That a pole is the member which is having its longitudinal dimension or length much larger than its cross-sectional dimensions. For example, an electrical pole, or for example, that electrical pole is having the cross-sections very small, whereas the length is around 17 to 18 meter. So we can say this is a pole, and an axis along this length is called polar axis, and the moment of inertia about that axis is called polar moment of inertia. This is the polar moment of inertia. You can say this is the section. These are two axes, and this is the cross-sectional axis, the length which is passing through the point of concurrency of these two. So this is the one. So you can say that Z, that is JO equal to IX plus IY. Yeah. Now next comes your parallel axis theorem. Parallel axis theorem, it states that the moment of inertia of a section about an axis will be equal to the moment of inertia, sum of the moment of inertia about its centroidal axis plus the square of the distance between centroidal axis and the reference axis, and into the square of the this, and multiplied by the area. For example, IA will be IB plus D square into area. This is called a parallel axis theorem. This derivation we have done in the last lecture. So again you can say that IA equal to y square d integral y square d, then y can be taken outside, y square d, then y square can be written y dash plus a. This is y dash, this is a. So this is d. Y dash plus d whole square into d. So y dash square dA integral plus 2a y dash dA plus d square integral dA. You can say this term is the moment about centroidal axis of the plane or complete plane, that is y dash dA. dA is the area into perpendicular distance from this centroidal axis, from the axis of reference. Here axis of reference and centroidal axis is the same, hence the y dash is 0, implies that this whole term is 0. So we can say that this is y dash square dA is the integral Ix. So IA equal to Ix plus d square into area integral dA. Integral dA means A, complete area of this section. Now radius of gyration or radius of a body about an axis of rotation is defined as the radial distance to a point which would have a moment of inertia the same as the body's actual distribution of mass if the total mass of the body were concentrated. It is a measure of distribution of mass about the given axis. If the particles of body or distribution of mass is near to the reference axis, then its moment of inertia will be less, and if it is away from the reference axis, then its moment of inertia will be more. The knowledge of mass and area and radius of gyration, if available, then we can find its moment of inertia without knowing its actual shape. So, if we don't know the shape of the body, but we know its radius of gyration, then we can find out what is its moment of inertia. The derivation is not required here because it has been discussed earlier. So, moment of inertia of a composite section. Now, we are dealing with the composite section. Here, we have to understand these 4 steps before we commence onto the actual problem. The moment of inertia of composite section may be found out by the following step. First of all, split the given section into plane areas, that is rectangle, triangle, circular shape, etc. Find the center of gravity of these sections. Then find the moment of inertia of these areas about their respective centers of gravities or centroids. Then now transfer these moments of inertia about the required axis AB by the parallel axis form, that is IAB equal to IG plus H square, where IG is the moment of inertia of a section about center of gravity and parallel to the axis, A area of section, S distance between the required axis and center of gravity of the section. The moment of inertia of the given section may be now be obtained by the algebraic sum of all these moment of inertias so found. You can say like this, okay, we can go to the actual problem. This is the problem we are going to solve. Example, we have to find out the moment of inertia of this L section. This is the L section. We have to find out the moment of inertia about the axis KK. This is the KK axis. We have to find. So first of all, we split this L into 2 rectangles. So we have split it into EF D. Okay, I am telling it G, DG, and AGCB. EFDG and AGCB. This is the AGCB, this is the other one. Now, for this section, IK will be IK1 plus IK2. The point number 4, that add up the moment of inertia of the if we know IK1 and IK2. So first IK1 refer to this second equation, IK1 is equal to IG1 plus A1 into K1 square. K1 is the centroidal distance distance of centroidal axis from the axis of reference. We have considered it is K1. So this is the K1, this is the K1. Hence, similarly for section 2, rectangle 2, that its centroid will be somewhere here, 240, half of 240, 120 plus 100. This K2 will be 220. Okay, so we just apply it directly with this IK equal to, this is your IK1 and this is your IK2. How? Just let us discuss it now. I G1. How much will be? This is the axis, so BDQ by 12. Here 120 is the total length from here to here. 120 it is given here into 40 cube. 40 cube. I told you earlier that we have to make a cube of the dimension which is perpendicular to the axis of reference. So here axis of reference is this one, the axis of reference, its vertical dimension to this is this 40. So 120 into 40 cube by 12. It is the centroidal moment of inertia of section 1 plus this A1 K1 square. A1 K1 square. Area 120 into 40 plus K1 means how much? 100 plus 20. This is a 40. Its centroid will be in between. That is half of 40, 20. The 20 plus 100, 120. So what is 120 into 40 into 120 square. This has become the moment of inertia of section 1 about Kk plus moment of inertia of section 2. How much it will be? First, its centroidal axis is this much. So its area is, well, first BD cube by 12. Here cube is of this dimension 240. So 40 into 240 cube by 12, it is moment of inertia of its centroidal axis, this axis, plus its length from here to here, that is square of that into area of this, that is plus 240, this is the 240 into 40, this is the dimension 40, this is the area into 220, that 120 this plus 100 this, square of 220. On calculation, it will come 69.76 into 10 to the power 6 plus 510 into 10 to the power 6. Total comes out to be 580.48 into 10 to the power 6 millimeter to the power 4. Next, another problem will clear you furthermore. This is a bit complicated problem. Here, determine the moment of inertia of the area shown shaded in figure 8.18 about the axis x-axis which coincides with the base edge AB. This problem I had taken from the textbook Engineering Mechanics by Dr. D.S. Kumar. So here what we have to do, we have to apply a concept that first of all find the moment of inertia of whole this rectangle about x-axis and then reduce the moment of inertia of this semicircle from the rectangle moment of inertia about the same axis. So first of all find the centroids of this, that for a rectangle centroid will be somewhere here in the center, that is 1.25 centimeter away from the axis x-axis, and for this it is the centroid which is 4r upon 3 pi from the top. This is 4r upon 3 pi from the top, that is DC. For the time being, for this, just to remember this much. That is like this, and then in the next class I will give a derivation for this, how it is coming 0.11 r square and 4r upon 3 pi. So the given section comprises of full rectangle ABCD minus the semicircle DEC. Moment of inertia of rectangle ABCD about AB is found out by applying the parallel axis force, and it comes out this is IG G plus A1 H1 square is equal to 2.2 into this is 2.5. So square is of 2.5 because the cube is of 2.5 because it is perpendicular to the axis of reference. So 2 into 2.5 is cube divided by 12 plus 1.25 cube ka square here into area, that is 2 into 2.5. It comes out to be total 10.416 centimeter square. This you could have found out directly also, that I AB will be BD cube by 3 for a rectangle, and by method of integration you could have found out 0 to h integration करने के बाद मिल जाएगा आपको ये. So then also this would have been the same answer, 10.416. The moment of inertia of semicircle about AB, that is IZ I2 a section 2 I2 equal to IG2, that is moment of inertia about its centroidal axis, plus A2 H2 square. Here this is 0.11 r square plus half pi r square is the area into 2.5 minus 4r upon 3 pi whole square. I told you that this is the distance 4r upon 3 pi. In the you can find it out very easily. Then total will be I2 equal to 0.11 into 1 square plus half pi into 1 square into 2.5 minus 4 into 1 upon 3 pi whole square, that is 0.11 into 6.76. It comes out to be 6.87. So total moment of inertia is the moment of a rectangle minus moment of inertia of semicircle, that is 10.416 minus 6.87. It comes out to be 3.546 centimeter to the power 4. Now next problem, determine the moment of inertia about centroidal axis xx and yy of the channel section shown in figure 8.20. This problem is again taken from the same textbook. Here first of all you have to find out the moment of inertia about the centroidal axis. So these are the centroidal axis. First, now first of all find their respective centroidal axis and then apply the parallel axis for sum of these. These are the 3 steps we are going to take in one by one. Here the section is divided into 3 rectangles, that is 1, 2 and 3, like this. 1, 2 and 3. That A1 10 into 1.5 15 centimeter square. Then A2 40 minus 1.5 minus 1.5. This is the total length is 40, this 1.5 here minus 1.5 here minus, total is 37. So 37 into 1 is comes out to 37 square centimeter here. Then A3 is the same as A1, again 15 square centimeter. Add all these three, total area becomes 67 centimeter square. The given section is symmetrical about horizontal axis. It is symmetrical about this axis. So the y dimension is automatically reduced to be 0 here. The distance of centroid of section with reference to section 1 is summation Ax upon summation A, which comes out to be 2.51. With reference to centroidal axis xx and yy, the centroids of rectangles are as given below. 5 minus 2.51 and 40 by 2 minus 1.5 by 2. That is 2.49 and 19.25 for A1. This is, you consider this 0.75 here plus, that is 40 minus 0.75. The distance this much. Same is for this much. And this is line on this, so it is 0. These are the dimensions of y. And x dimension, from here it is coming 2.51, this is 2.51. So this is 2.51. So 5 minus 2.51 is the distance this much. Same is the distance this much. That is 2.49. This distance is 2.49 for this and this. And for this, that is 0.5, it is 1 centimeter, it is just minus 2.51. So 0.5, it is 2.01. So here is the 2.01 and 0 for A2, this 2.49 and 19.25 for A1, same is 2.49 and 19.25 for the A3. The invoking parallel axis thought, the moment of inertia of areas A1, A2 and A3 about the centroidal axis is find out like this. That is Ixx 10 into 1.5 cube by 12 plus, by applying the parallel axis theorem, 15 is the area into 19.25. 19.25, this is 19.25. Then 1 into 37 cube by 12, because its center is already on the centroidal axis. This area number 2. If you can consider this like this is the block, the channel section. So this distance is 2.5 from here, it is 2.5. So this This is already, its centroid is lying on the same x-axis. So this is done, and this is equal to this, both are same. So it comes out to be 1553 point. How much this is? 155343.58 centimeter to the power 4. This is all. Similarly, for IYY 1.5 into 10 power 3 by 12 into 15 into 2.49, that is 1.5 into 10 cube by 12 plus 1.5 into 2.49 square. This is for area, top area. For this one, same will be for this one, and we are to concentrate for this, the 37 into 1 cube by 12. It also comes out to be, on calculation, 439.08 centimeter to the power 4. Thanks for watching this video lecture. The references are Engineering Mechanics by Dr. D.S. Kumar, Engineering Mechanics by R.S. Kurmi, and Google search engine.